As you can see here, we're talking about finding the area of a region bounded by two curves. But as we get started, I want to first discuss, to do some introductory work, pardon me for stuttering there, do some introductory work that will make our job a little easier, not only for this section, but for sections in the future. So I want us to first note about how we find the height of a vertical rectangle. And so let me just give you a little quick example here so that I can say it more generally. Suppose we have, of course, an XY coordinate axis, and suppose this is where 1 is, and this is where 2 is, and this is where 3 is, and this is where -1 is, and this is where -2 is. And suppose we want to know the height of the rectangle that I'm drawing in here. Now, in this case, of course, we can count the height. We can start down here where the rectangle begins. There's 1 unit, 2 units, 3 units. But note here, the way we do this is we'll take the largest y value, that's right here, and subtract the smallest y value, and of course that's right here at -2. And when we say 1 subtract -2, of course we get a +3. So what we see to calculate this height, and that's what we're wanting to do, we take largest y subtract smallest y. So in general, okay, just in general, if we have some kind of rectangle sitting on the XY axis, okay, and we recognize that this is the top of the rectangle, if you will, and that's at a y value y sub 2, and the bottom of the rectangle is at y sub 1, where y sub 2 is the largest y value, then this height can be calculated in this fashion. It's simply y sub 2 minus y sub 1. Now, we're going to see a need in the future also to calculate the height or the length of a rectangle that is horizontal. Of course, above is where it's vertical. So we could go through the same kind of argument, and it wouldn't be difficult for us to make this decision, but suppose we have a rectangle that is laying on its side, okay? So a rectangle like this. So this length, okay, the length that we're talking about here, how would we calculate this length? Okay, well that length would be the largest x value. Well, here's the largest x value. I'm going to call that x sub 2. And here's the smallest x value, x sub 1. So this, as we're reading from left to right, we're going from x sub 1 to x sub 2. So that length will be the largest x value, subtract the smallest x value. And that's how we would calculate the length in that case. Well, this is going to pay off for us in the future. And in fact, what I want to do next is I want to review how we calculate the area under a curve, and then remind you the idea behind it, and then we'll kind of smooth that out and get a thinking for how we'll do things in the future. Okay, so we're asked to find the area of the region bounded by y equal x squared plus 1, y equals 0 as a line, which is a horizontal line, and x equals 0 and x equal 2. Well, x equals 0 and x equal 2 as lines, or vertical lines. We're talking about an area, a region that's enclosed by these particular pieces. And so we remember in the past the way we should start a problem like this is we should sketch the graph of what region we're trying to find the area of. So let's do that real quickly and then discuss further. Okay, so let's suppose, 1, 2, 3, 4, 5. Okay, that'll be just about perfect. 1, 2, 3, 4, 5. And I'm going to kind of spread this out along the x-axis so I don't really have the same scales. There's going to be 1 and there's going to be 2. It's just so that I have room to make this sketch. Well, we know that y equals x squared plus 1 is a parabola that has its vertex moved up 1 unit, and so the vertex would be here. And we know that when x is equal to 1, then y would be 1 squared plus 1, which would be 2. And when x is equal to 2, y would be 2 squared plus 1, which is 5. And so we would end up with a parabola that looked like this on the right side of the y-axis, pardon me. Now, remember the boundaries. Okay, so this is the curve y equals x squared plus 1 that we see, but it's also bounded by y equals 0, which is nothing more than the x-axis, and the vertical line x equals 0, which is here, and of course x equals 2, which is here. So we're being asked to find this area bounded by those 4 lines, or curves, and that's nothing more than the area under the curve. So you recall the way we would do this is that we would calculate the area using an integral. And it would be the integral from the lowest x value of 0 to the highest x value of 2 of the function itself, x squared plus 1, with respect to dx. Now, when we first learned how to do this, what we really were introduced to was the idea of breaking this region into multiple rectangles. Okay, lots and lots of rectangles. And let's see how I've done this here. I'm kind of messy with the work that I've done. Okay, but we have all these rectangles, and we summed up the area of each of those rectangles, and then we let rectangles get in smaller width, so there were more rectangles. And then we let the rectangles get even smaller width, so there were more rectangles. And of course, each time the rectangles' widths got smaller and we had more rectangles to work from, then we actually got a better approximation for the area. And so we let the width of those rectangles go to 0 by taking a limit. Now, it's going to be convenient here to recognize, let me just sketch this again real quickly and not be quite as accurate as I was before. So this is what we're talking about. This is the region that we're talking about. Let's look at one single representative rectangle, okay? Now, let's assume that it is infinitely small in width. And when we come up here and recognize, of course, the height of this rectangle is nothing more than the y that's defined by this curve. And that y, of course, is x squared plus 1. So that y value is the height of the rectangle. And the width of the rectangle we call dx, okay? The width of this rectangle, dx, it's an x length, but it's infinitely small, or it's going to be infinitely small. And so if we come up here and think about this integral, then this part of the integral is the height of the rectangle. And this part of the integration, the integral we set up, is nothing more than the width. And so we can think about that as a product of the height and width. So together, that is the area of that one single rectangle. And and this is not difficult for us to do, but I want you to think about how we're going to think not only for calculating these areas, but this will serve us a great deal for later things in this course that we'll do. Let me pause right now for just a second and let me get something to wet my throat. Well, here's the way I would like us, and I'm going to remind us as we do these things many, many times. Generally, we need to think of definite integration as a way to infinitely sum, that is, add up an infinite number of things, and each of those things has some infinitely small measurement. So in the case here as the area under the curve, we have an infinite number of these rectangles inside the region that we're trying to calculate the area of. And we represent one of those rectangles. Well, that rectangle has a measurement of width that is infinitely small, because that's what we're letting happen, is we're letting those rectangles get smaller and smaller widths. And as the widths get infinitely small, the number of rectangles gets infinitely large, and that's how we use integration to add up that infinite number of rectangles, each of which has an infinitely small width. Now, we're going to use integration to do a lot of things, and if we can think in these terms, it will help us build the integrals to solve the problems that we want to solve. But this section is about finding areas between two curves. And so we'll begin on the next page with an example of that and using this concept that we just talked about. Okay, you can see the problem that we're working on here is stated in this fashion. Find the area bounded by the graphs of y equals square root of x and y equals x squared. Now, many times the hardest part of these problems is interpreting what is we're supposed to do. We know we're supposed to find an area, but what area is that? I mean, we just have two curves given to us. So I'm going to give you an idea the way I'm going to act like I haven't really know what I'm doing, and so I'm thinking, okay, well, let me look at these two graphs, and just, this is rough, okay? I want you to understand that this is not really the way that I would finish this out, but I want you to see my thinking, or the way you may think. Well, let's see, y equals the square root of x is a graph that looks something like this. And y equals x squared is a graph that looks something like this. Okay, now that's real rough. And we're supposed to find the area bounded by those two graphs. So what we have to recognize is that we're looking for a region that is enclosed, that is surrounded by these graphs. And if you notice here, this is that region that is surrounded by those graphs. And so that's the area that we're being asked to find. Now, once we understand that, then we need to be a little more careful by the way we put together our graph. So notice that I don't really care about things that are in the second quadrant. This entire region that I'm finding the area of falls within the first quadrant. And I'm going to be a little more precise now as I draw the graph, okay, of the region that we're looking for. Now, here's what I know, and I mean, I'm thinking I've got to figure out where this intersection point is. I've got to understand what these values are, I suppose. And I know that, let's just think about this. I mean, what we could do is find out where those two graphs intersect. And the way we would find out where the two graphs intersect is finding out where x squared is equal to the square root of x. And so if we solve that equation, then we could do it. Now, this isn't quite as easy as it may sound, and we might not really need to go through this trouble. Well, let's suppose that this is what we're trying to do. Well, we would like to be able to get rid of the square root of x. Well, in fact, let's do this. Let's write this as x squared minus the square root of x is equal to 0. And then we can say, oh, that's x squared minus x to the 1/2 power is equal to 0. Now, that would allow us, I suppose, to factor this to some extent. But I don't know how much good that's going to do us. Let's say, okay, the smallest power of x that we can factor out is x to the 1/2 power. And so that would leave behind x to the what? 3/2 power? Because when I multiply x to the 1/2 with x to the 3/2, I get x to the 4/2 or 2. Minus 1 equals 0. Okay, now, how does that help us? Well, what causes that to be true? Well, x to the 1/2 can be 0, which means the square root of x is 0, which would mean x has to be 0. And so that's this x value that we're talking about there. What's the x value that we're talking about here? Well, that would happen when x to the 3/2 power minus 1 is equal to 0. See, we have two factors, and we would set each of those factors to 0. Well, how can x to the power be equal to 1? Well, let's look at this a little differently. What does x to the 3/2 power mean? Well, that's really the square root of x cubed, isn't it? So we have the square root of x cubed minus 1 is 0, or the square root of x cubed is equal to 1. And the only way a square root can be equal to 1 is if x is what we're taking the square root of, in fact, is 1. So that means x cubed would have to be 1. And of course, the only way x cubed is going to be 1 is if x is equal to 1. And so we find out that this x value is 1. The x value here, of course, we already knew was 0. So that allows me to make this graph a little bit better. And I suppose that I could have done this a little differently anyway. Let's suppose this is where 1 is on the y-axis. When I'm graphing y equal x squared, for instance, when x is 0, y would be 0, and when x is 1, y would be 1, and that would be these points. And so that graph would look something like this, wouldn't it? Okay? And then it's going to go on from there and go this direction. Now, when I'm graphing y equal the square root of x, if x is 0, y is 0. On the other hand, if x is 1, y would be the square root of 1, which is 1, so it also goes through this point. But that graph, of course, the square root graph looks like this, doesn't it? And then it would go on from here. So we may have done that without all of the work that I've done here, just because of our knowledge of graphs. Now, that's the region that we're trying to find, the area of. Now, here is the approach that I would like you to practice. Draw a representative rectangle. Now, from that one representative rectangle, we can calculate the area. So let's take that one representative rectangle and think, and I'm expanding it here. Now, we think of it as being infinitely small in one dimension, and that would only be this width dimension. And so when we're talking about the width dimension being an x dimension, then as infinitely small, I'm going to call that dx. Now, the height of that rectangle is the next question. And remember, the way we find the height of a rectangle is we take the largest y value. Well, in this case, the largest y value depends on the curve that's the square root of x. So the largest y value is the square root of x, subtract the smallest y value. Well, the smallest y value happens to be on the curve y equal x squared. And so that smallest y value is x squared. So that ends up being the height of the rectangle. So the area of that one small rectangle of the small rectangle, okay, would be the height, which is the square root of x minus x squared, times the width, which is dx. So that's the area of the tiny rectangle. Now, we have an infinite number of those rectangles, and so we're going to add up all of the areas of each of the rectangles to get the total area. But since we've got an infinite number of them, that's the way we use integration. Now, the first rectangle we have will start at the value x equals 0. So the very first rectangle is going to be starting right over here, isn't it? And the very last rectangle we're going to have is when x is equal to 1. And so we're adding up all the rectangles between x equals 0 and x equal 1. That is not the rectangles, but their areas. And each of their areas is the square root of x minus x squared dx. And so from there, then we can calculate the area. And I'm not going to go through the trouble here. Well, I guess I will in this example, but in the future I may kind of spread this out and just give you an answer. I'm going to write the square root of x as x to the power 1/2 so that I can easily integrate. Now, to do a definite integral, we first figure out the indefinite integral. So the indefinite integral of x to the 1/2 power, what do? We increase the exponent by 1, and we multiply it by the reciprocal of that new exponent. So when we increase 1/2 by 1, we get 3/2. 1/2 plus 1 is 3/2. And we offset that by the reciprocal of that new exponent, which is 2/3. And of course, we increase the exponent on x squared by 1, we get x cubed. And we offset that new exponent with a factor of 1/3, the reciprocal, in front. So that's the indefinite integral. Now that's what we have to evaluate from an x value 0 to an x value 1. But remember, we first substitute 1 in for the x's, and then we substitute 0 in for the x's. So when we substitute 1 in, we'll have 2/3 times 1 to the 3/2 power minus 1/3 times 1 to the 3rd power. And then from that, we subtract what we get when we substitute 0 in for x. Well, that'd be 2/3 times 0 to the 3/2 minus 1/3 times 0 to the power 3. Now, of course, over here, 0 to any power is 0, and so all of this part ends up just being 0. And so our real issue is, what do we have here? Well, 1 to any power is 1, so we end up with a 2/3 times 1 in the first position, minus 1/3 times 1 in the second position, and of course 2/3 minus 1/3 is simply 1/3. And here we're talking about area, so it's 1/3 square units, whatever our units of measure are here. So the most important part was not the integration part, it's how we set up the integral, how we build the integral by thinking of infinitely small pieces that we have an infinite number of that we add up by using integration. Okay, we'll look at a second example here in a moment. Let me pause temporarily as we go to that second problem. In our next example, you can see what we're being asked to do. Find the area of the region bounded by the graphs of y equal x squared plus 2x, y equal negative x plus 4, the vertical line x equal negative 4, and the vertical line x equal 2. Now, once again, the setting up the problem is not usually too difficult if we know what it is we're actually trying to accomplish and what area we're talking about. So we always have to spend some time looking at a graph of the region, actually illustrating the region. So but let's do a little bit of work. We recognize that y equal x squared plus 2x is a parabola. And a couple of things that would be nice to know about this parabola is where's the vertex and what are x-intercepts. Well, x-intercepts are pretty easy to find because x-intercepts are the x value that causes y to be 0. So we'd be looking at, assuming y is 0, what x's would cause that to happen. You see, we can solve that equation very quickly because the right side factors nicely. And so we would get x equals 0 and x equal -2 as the x-intercepts of the parabola. Now, what else would we need to know? Well, the vertex. Now, the vertex, and we happen to know this parabola opens upward, don't we? Because it has a positive leading coefficient in front of x squared. The vertex is a local maximum or a local minimum. In this case, it's a local minimum. And so it would be useful to find y prime so that we could find out where y prime is 0, and that's where we have a vertex, a local minimum, relative minimum, or relative maximum. So y prime is what, 2x plus 2? And so when is that 0? Well, that's 0 when x is equal to -1. So the vertex, okay, has an x value of -1, and we would simply calculate the y value by putting -1 into the function, of course. Oops. And we would end up getting what? Y is equal to 1 minus 2 or -1. Okay? So the vertex happens to be -1 comma -1. Now, while we're here, I'm thinking, well, let's set up to graph this. So let's assume here is where y is -1, here's where y is 1, 2, 3. And actually, I think I'm going to reassess this. Let's make these in units of 2. Let's call this 2, 4, 6, 8. And I think you'll see why I've done this here in a moment. And of course, let's make this -2 and this -4. And of course, we needed to go to -4 for our x value, didn't we? And we need to go to positive, 2 for our maximum x value. So let's say that's where positive 2 is. Okay, so -1 would be approximately right here. Let's just call that. And we decided that it crosses the x-axis at 0 and also at -2. Now, when x is -4, what y would we get here? Well, we would have what? -4 squared plus 2 times -4, which is 16 minus 8, or 8. And so that's really the reason that I've done that. And when x is positive 2, okay, then what would y be? And we could calculate that real easily. Y would be well, let's see. I'm sorry, I've had a little senior moment there. Y would be 2 squared plus 2 times 2. So that's 4 plus 4, or 8. So it's up here. Okay. And so we get some rough idea of what the parabola looks like for the x values that we're interested in. Now, we've dealt with this graph, but what about this graph, y equal -x plus 4? Well, that's pretty simple. That's a line that crosses the y-axis of 4, doesn't it? When x is 0, y is 4. And we know it has a negative slope a -1 slope, and so we could calculate some other pieces here very easily. But let's just let's imagine if x was -4, then if x is -4, then y is the negative of x plus 4, which would be 8. So the line goes through this point also. Now, when x is +2, and why am I worried about that? Because we're going from a -4 to a +2. So when x is +2, we would end up with y is +2 as well, -2 plus 4. So it goes through this point. Okay, so as a rough sketch, this is what our line looks like. Oops. Now, remember, we're wanting to know the region, the area of the region bounded by these two graphs and the line x equal -4, which is this line, and the line x equal +2, which is this line. And so that really gives us this little piece right here. So we're looking at, if you will, the area of the region that I've shaded real lightly there. And you see that region is really broken into two parts, isn't it? We might call this region, its area, we might say is A1. And then this smaller region, we might say its area is A2. Now, we could calculate the total area. By the way, the total area that we're interested in is going to be the area of the first part of the region, A1, plus the area of the second part of the region, A2. Now, to calculate A1, the area of the first region, we're going to integrate, we know that, okay, and we're going to, let's look at a representative rectangle in this region. Well, there's a representative rectangle. Now, we need to know the height of that rectangle, okay? And so, in this representative rectangle, the highest part is a y value that's defined by the line. And so that's -x plus 4. And the lowest part, okay, of this rectangle, or any rectangle in that region, is a y value that's defined by the parabola. So y is x squared plus 2x. And remember, the height of that rectangle then is the highest minus the lowest. And so we would be integrating that the height of that rectangle, let's make sure that we understand that. The height of that rectangle is going to be -x plus 4, that's the highest y, minus the lowest y, x squared plus 2x. Okay, so that's the height of the rectangle. Now the width of this rectangle, remember, we're making them infinitely narrow in the x direction. Okay, so the width is infinitely narrow, and that's why we call that dx. And so that's the width of that infinitely representative rectangle. Now these rectangles, we're going to start over where x is -4. But you notice that things change after we go past this particular position right in there. And so we need to know what x value that is. Because when we get on the other side of that x value, notice that the parabola is on top and the line is on bottom. Parabola is on top and line's on bottom. And so we have a change in what the highest y and the lowest y is. So we'll do a different subtraction. Well, we need to find that point of intersection. we do that, we'll have our limits of integration set. Well, where two graphs intersect is where what x's cause their y's to be the same. And so one has a y of x squared plus 2x, and we want to know where it is the same as the y on the other graph, when the y on the other graph is negative x plus 4. So we need to know when those two are equal, the solutions to that equation. Well, we can see that if we add x and subtract 4 on both sides, we'd have x squared plus 3x minus 4 equals 0, which is a quadratic equation. And in this case, I think we can factor the left side. How about x plus 4 times x minus 1? I believe that'll do it. And so we get x equal negative 4 and x equal positive 1. Now, negative 4 is the x value that we've got right here. The positive 1 is the x value that we have here, which is the other point of intersection. So those are the 2 points of intersection. So this upper limit of integration is an x value of 1. Well, now we ought to be able to do this integral fairly routinely. Okay. Inside, we actually have a negative x plus a 4 minus an x squared and minus a 2x, and we distribute that negative sign. And of course, that ends up being the fact that we're going to be integrating what? Negative x squared minus 3x plus 4 from negative 4 to positive 1. And let's see what calculation we get here. When we get the indefinite integral of negative x squared, that will be what? Negative 1/3 x cubed. And then we'll have minus 3 halves x squared and plus 4x. And that we have to evaluate from negative 4 to positive 1. This is being a little more work than I was anticipating. So first we substitute in a a 1 for all of our x's. And when we do, we'll get a negative 1/3 minus 3 halves plus 4. And from that, we'll subtract what we get when we substitute in a negative 4 for all of our x's. And in that case, we'll have negative 1/3 times negative 4 cubed, which will be positive 64 over 3, I believe. And then we'll have minus 3 halves times a negative 4 squared. Well, when we square negative 4, we get 16. And so that ought to be, what, 3 halves times 16? So that ought to be 24, I believe. And then finally, we have a plus 4 times negative 4, because our x is negative 4, which will be, what, minus 16? I'm going to do a calculation on the side. Let me pause for just a moment. Okay, so my calculation tells me that that's 125 over 6. But remember, that's the area of the first region. Now, let's go to the next page and calculate the area of the second region so we can calculate the total area. And let me kind of re-sketch the graph over there real quickly. Okay, I've done a real rough sketch of what we were seeing on the last page right here. And it's not to scale, but I wanted to make enough room so that I could actually get this part in here. Now, before we go on calculating the area of the region enclosed in the second part, so that area we're calling A sub 2, I want to point out to you that in the first part of the problem, we calculated the height of this rectangle, and we didn't really care where that rectangle fell. That is, here we have part of the rectangle above the x-axis and part below the x-axis. All we really cared about is taking the largest y value and subtracting the smallest y value to actually get the length of the rectangle. And that doesn't matter whether the rectangle is all above the x-axis, all below the x-axis, or some above and some below, which it tells us that we don't really have to care about where this region lies. Not like what we were doing when we had the area under a curve, and we would worry about sometimes getting a negative value for our area. We're just finding a positive height of that rectangle, and that's an important concept to realize. Okay, well, in this region, we look at a representative rectangle. Okay, so what we need to do, now remember, this is where x is equal to 1, and this is where x is equal to 2. That was what we had on the other side, on the other page. Now, so we're going to set up a integral here to calculate the area of this second region. In this case, though, we're going to integrate, we're going to start our rectangles at an x value of 1, and we're going to stop our rectangles at an x value of 2. But also what changes, the reason we're doing this in two parts, is the highest part of that rectangle is defined by y equal, what is it, the parabola, y equal x squared plus 2x. So when we're finding the largest y, it's x squared plus 2x. And from that, we subtract the smallest y, and the smallest y is the y that's defined by that straight line, which is negative x plus 4. And of course, dx. So once again, this is the height, okay, and this is the width of that rectangle. And when we multiply those two together, we get the area. And so we have the area of one representative rectangle that is infinitely narrow, and where the integral is we're adding up all the infinite number of rectangles that we could have between 1 and 2. Now, this would work similarly to what we did a moment ago. We would do first some simplifying, and we would see that what we're actually integrating after we simplify inside would have x squared plus 3x minus 4. And then, of course, oops, my bad. When we find the indefinite integral, which would be 1/3 x cubed plus 3/2 x squared minus 4x, and we evaluate that from 1 to 2. Now, I'm not going to bore you with the work here. I'm convinced that you can do that. But when we do this calculation, we end up with 17 over 6. So remember, the total area is the area of each of these separate regions. And so the total area would be a sub 1 plus a sub 2. And in this case, what is that? 125 over 6 plus 17 over 6, which ends up being 142 over 6. And that will goes into 142 and a 6, so that's 71 over 3 square units. Now, after you get a little bit used to how these things work, we could have done this all in one setup. We would have still had two integrals, but it might have been a little easier from the very beginning. Anyway, let's look at another note here. Just a moment. Let me set up for this other note. Okay, as you can see here, the point I'm trying to make, and I referred to it a bit in the last problem, that this new method, this new idea, it's not really new, but and that method being, look at a representative rectangle. So here I've got a representative rectangle, okay? And when we look at a representative rectangle, if we calculate the height of the rectangle by taking the highest y value and subtracting the lowest y value, this method will ensure that we don't get a negative result when we calculate area. And as you recall, in a problem like we see here, if we just went about, let's suppose this is where x is A and this is where x is B, we had to worry about when we did the integral for calculating this area that because the area lies below the x-axis, the result we would get is negative. But here, now if this curve is defined by f of x, okay, well, what we would end up doing is we would calculate the integral starting at x values of A and going to x values of B, and our representative rectangle has a height. Well, the highest y value is always the same, okay? The highest y value is always on the x-axis, and y values on the x-axis are 0. So the largest y value, the top of that rectangle, is at y equals 0. And the bottom of that rectangle, so we take the highest y and subtract the lowest y. Well, the bottom of that rectangle is the y that we get from whatever the definition of the function is. So this is the height of that rectangle. And of course, the width of that rectangle, whoops, not d, w dx. This is the width. Well, then this method is going to ensure that when we calculate that area, we actually have the integral from A to B of negative f of x dx, which is the same as the negative of the integral from A to B of f of x dx. And so this negative that we see here ensures that when we calculate this integral, we'll get a negative, but we're taking the opposite of that. That's why it ends up being positive. So our new technique, our new way to look at this, by just actually calculating the height of the representative rectangle, will ensure that our result is always positive. And when we go way back up here to the problem we were looking at a while ago, see that rectangle is partly above and partly below, but as I discussed earlier, the x-axis that is, all we're doing is calculating height. So we take highest y value and lowest y value, and that's the way we'll calculate that height. And those y values depend on the function that defines the graph that we're at. Okay, well, on the next problem, which I'll do on the next page, I actually want to do it two different ways because the standard way causes a little bit of grief here. As you see here, we're to find the area bounded by the graph of y squared equal 1 minus x and the graph of 2y equal x plus 2. And this problem has its own issues. One, the 2y equal x plus 2 is written a little strangely, but more strangely is the fact that we have y squared equal to 1 minus x. And you know, that's I hope that we recognize from pre-calculus that's actually a parabola that is opening left or opening right rather than a vertical orientation up or down. This is a horizontal orientation. And you know, we can go through a lot of trouble to figure out the orientation that we would need, but let's just start thinking about it for a moment here, and we'll graph this. Now, we could just think about plotting some points, and as we do, then we would come up with some kind of idea here on what this might look like. And so, for instance, we could choose an x value of, let's say, 0. Oh, let's say an x value of 1. Say an x value of 1. Well, then y squared would be 1 minus 1 or 0, and so that would tell us that y has to be 0, doesn't it? Okay. Now, what I'm wanting to point out here is we can't have x bigger than 1. For instance, if x was 2, we would have y squared as 1 minus 2, or y squared is negative 1. And of course, when we square y, we're not going to get a negative value. So 1 is the largest value of x. And now we can choose x to be 0, and we'd have y squared is equal to 1. And that means y can either be plus or minus 1. So we actually have the point 0, 1 and the point 0, -1 both on this graph. Let me just kind of speed things along. I suppose if we let x be equal to -3, then we would have y squared is 1 minus -3, which is a 4. And so y would be plus or minus 2. And I'm going to jump clear out to -8 just for now. And so y squared would be 1 minus -8, which is 9. And so y would be plus or minus, would be equal to plus or minus 3. Okay, so let's graph this parabola. And I'm not going to try to be perfect in my graph, but let's at least have something that is reasonable. And just, I need to get some idea of what this graph looks like. And so I'm going to, let's say this is where 1 is for x. And of course, in that case, y is 0, and there's only one y value. And then when x was 0, y could be positive 1, okay, or y could be -1. So 0, 1 is on the graph, and 0, -1 is on the graph. And now we can see how the graph is actually going to be opening. It's going to be opening to the left, isn't it? And I know it's not to scale, but let's suppose this is where -8 is. And so here would be roughly, here would be roughly -3, and here would be roughly +3. And so -8, -3 is on the graph, and so that's about down here. Okay. Well, okay, that doesn't look too good, but, and of course, it's going to come up here like this as well, okay, but I kind of know where I'm headed now. Let's look at this line, okay, let's look at 2y is equal to x plus 2. We could easily solve that for y by multiplying through by 1/2 or dividing both sides by 2. I prefer to think about multiplying through by 1/2. So we have y is equal to 1/2 x plus 1. And then we do recognize that, of course, as a line. Of course, the y-intercept is 1. So it goes through that point. Now, it might be useful to notice that when x is -8, then y, notice here, if x is -8, then y is 1/2 times -8 plus 1. And that's -4 plus 1, which is -3. So it goes through this same point right there. And I was fortunate enough to know that in advance. So here, whoops, play like that's a straight line. I apologize that that's not very straight. So we're trying to find the area of this region. Now, the problem is that when we start, and of course we know the important pieces here, but the problem that we have is that notice if we draw a representative rectangle here, okay, then the top of the rectangle is defined by the straight line, and the bottom of the rectangle is defined by the parabola. But as soon as we move past x equals 0, that is, as soon as we get to this part of the region, the top of the rectangle is defined by the parabola, and so is the bottom. And so to calculate the height of that rectangle is a different calculation than the height of the rectangle in the first portion. So I'm going to come back and think of this region having an area a sub 1 and this region having an area of a sub 2. And so the area that we're looking for, once again, is going to be a sub 1 plus a sub 2. Now, we still have a little bit of work here because this is a strange problem. I mean, the way it's defined is a little, the functions or the graphs are a little unusual to us. So here's what we have to be concerned about. For a sub 1, okay, we're going to set up an integral. And the integral is going to start with rectangles way over here where x is negative 8. So our beginning limit of integration is x equal negative 8. But these rectangles are only going to go to this position where x is equal to 0, because the way we calculate the height of the rectangle will change after that. Okay. Now, the top y in that region, okay, so the largest y, well, the largest y is defined by this line. And that y value we calculated a while ago, it's right here, isn't it? That y value is 1/2 x plus 1 minus the smallest y value is right here, and it's defined by the parabola. Now here's the problem though. What is that smallest y value? And we have to think about this a little bit. Now remember that parabola is defined by y squared equal 1 minus x. And we're looking for the smallest y value. We're looking for y that's defined by the parabola. Well, I kind of made myself kind of in a bind here. Well, this tells us what y squared is. Y, remember, is plus or minus, says y squared is 1 minus x, y could be plus or minus the square root of 1 minus x. And that makes sense to what we did a little earlier, because when we chose an x up here, we got two y's, a positive and a negative, didn't we? So it makes a little bit of sense about what happened. Now, the problem is, though, which is it in this particular case? Well, the y's down here, see, these y's are the negative y's. Y's up here, okay, are positive. Well, which y's are we interested in? We're interested in the negative ones. So for us, for that lowest y value, it's the negative of the square root of 1 minus x, not just the square root of 1 minus x. So we're subtracting the lowest y value, and the lowest y value is negative square root of 1 minus x. Okay. And then dx, remember, is that infinitely small width. So here is the height of that rectangle. Here is the width. And so we have height times width, if you will, for the area of that one representative rectangle. Now, that's going to take a little bit of work for us to do. And maybe I'll go through this one for you. In fact, I will. This is going to take some calculations for us. But let's do that. So a sub 1 is the integral from negative 8 to 0. And our integrand, that is what we're integrating, we need to simplify. So we have a 1/2 x plus a 1 subtract a negative square root of 1 minus x. So that will be a plus square root of 1 minus x. Now, we've got to do a little bit of thinking here to come up with this indefinite integral. And the indefinite integral of 1/2 x, well, what do? We'll increase the exponent by 1 and multiply by the reciprocal of that new exponent. Well, when we increase to an x squared, then we have to multiply by a 1/2, and we already have a 1/2, so that's a 1/4 x squared. And take the derivative of that real quickly and recognize we get 1/2 x, which we started with. And the integral of 1, of course, is just x. Now we have our work cut out for us. And so, although I don't have much space here, I'm going to come over to this part and look about how would we calculate the integral of the square root of 1 minus x. Eventually, I would expect you to be able to do this, and you'll just accept my result. But now, what we would normally do here is we'd think of that as 1 minus x to the power 1/2. And then we would use a u substitution. That is, we'd let u be 1 minus x. Now, that means we have the integral of u to the 1/2, but we have a dx. So we've got to deal with that dx. Well, remember the way we deal with that dx is we come up here where we said u is equal to 1 minus x, and we figure out what the derivative of u with respect to x is, and it's -1. So du is negative dx. So what we could do here is we could, if you will, we could multiply on both sides by -1 and get negative du is positive dx. So we could replace dx with negative du. In other words, we could put that negative on the outside of this integral. And that's something that we ought to be able to deal with. And of course, the integral of u to the 1/2 with respect to u is 2/3 u to the 3/2 power. But remember, we have the negative in front. And remember what u is. U is nothing more than 1 minus x, right? U is 1 minus x. So we end up with a negative 2/3 times u to the 3/2, but u is 1 minus x to the 3/2 power. And that we're integrating from -8 to 0. And since it's early in the semester, it's the reason I'm going through these details. Later on, I would just be mostly worried about setting this problem up. Okay. Well, I think, let me pause, and I'm going to do my own calculation here, and I'm sure that you can come to the same results, but I'm going to let you do that on your own. So let me pause, and I'll come back with the result. Okay, after I did my calculations, I got 28/3. Now remember, that's just the area of the left region. That's just a sub 1. So we still have work to do, don't we? We've got to calculate the area of the second region, or the right region. So let's go to the next page to do that. Okay, I'm looking only at the right region right now. Just so that we can concentrate on that and see what we've got. And of course, the graph is y squared equal 1 minus x. Now here's the important part to recognize. This part of the graph, that is this top half, which is all y values above the x-axis, well, that's y equal to the square root of 1 minus x. And down below, okay, down below this part of the graph are y values that are all negative. And so that is defined by y equal negative square root of 1 minus x. Oops, 1 minus x. So when we're calculating the area a sub 2, we're going to add up all of the integrals, all the representative integrals that we can have, but we're going to start our integrals when x is 0. See, when x is 0. That's along here. And we're going to stop those rectangles when x gets to 1. That's right here. So we're integrating from x equals 0 to x equals 1. Now, the highest part of a representative rectangle is going to be the y that's on top, and that's the positive y, which is the square root of 1 minus x. And remember, we subtract the lowest y. Well, the lowest y in this case is the one that's down here, and that y is a negative square root of 1 minus x. Okay, so here's the highest y, subtract here's the lowest y. And of course, the width of that representative rectangle is dx. So once again, this is the height of the rectangle, and this part is the width of the rectangle. And so when we multiply those two together, we're getting the area of that rectangle, one rectangle, and we're using the integral to add up the infinite number of those infinitely small width rectangles. Now, in this case, this will simplify to the integral from 0 to 1 of 2 times the square root of 1 minus x with respect to x. And I'm not going to go through this process completely. We would use substitution. Okay. I hope that you see, because we have the negative of negative square root of x, so that ends up being plus. So we have square root of 1 minus x, plus square root of 1 minus x. So we have two of them. So we could actually factor the constant factor of 2 out and work on just calculating this integral. And the substitution we would make is u being 1 minus x, just like we saw on the previous page. And when we do this, we should get 4/3. So the total area, and that's really what we're looking for, is the total area. What was it? A sub 1 plus a sub 2, and a sub 1 was 28/3, and a sub 2 was 4/3, and so we end up with 32/3, and of course they're square units, aren't they? So we're talking about area. Woo! That was pretty tough. Now, I want to show you an easier way. And this easier way, so it's a big or. We can do this much easier. What made this difficult? See, what made this difficult? Let's just stop and kind of get the idea again. It was difficult because when we used vertical rectangles here, the definition of how we find the height of those vertical rectangles changed as we moved from left to right. That they changed when x was 0, okay? And it was kind of a mess to do that. Now, no one says we have to use vertical rectangles. We could actually use horizontal rectangles. All we need to do is add up the areas of an infinite number of small rectangles. That is, small in one dimension. So let's go to the next page. Let me kind of repose our problem. We'll go to the next page and see how this same problem can be done differently. Okay, I've redrawn the rectangle. The diagram. Let me help you recall that we have y squared equal 1 minus x as the parabola. And we have, originally the way it was written is 2y is equal to x plus 2 as our straight line. That's the way it was originally written. Now, what I'd like us to think about, let's see, what is this point? This point is -8 comma -3. So we're talking about a y value of -3. Again, this isn't a scale. Don't be concerned about that so much. I'm just trying to get an idea. And this point right up here is 0, +1, isn't it? 0, +1. And of course, this is where x is 1. Here's where x, in this case, is -8. Okay. Now, Like I said, we've been drawing vertical rectangles. What if I instead draw a representative horizontal rectangle? Now just imagine these horizontal rectangles moving up instead of left to right, from low to high. So the rectangles are moving in this direction. And so we can sweep out all of those, okay? So we could calculate the entire area, and notice, no matter where we draw one of these rectangles, its left side is always on the line, and its right side is always on the parabola. So there's not a change. So this can be done with one integral. Okay? So let's think about how we would set up this integral. Okay? So the area is going to be adding up the total area is going to be using the integral to add up the areas of all of these little tiny rectangles. But this time we're moving from low to high. So what's changing are the y values, aren't they? We're going from a low y value to a high y value. Well, the lowest y value is -3. And the highest y value is +1. So we're going to integrate from -3 to +1. So we're thinking of these rectangles starting down here and moving in this direction. Okay? Now, this rectangle has a length that is left to right, and it has a height up and down. But the up and down height, see, that small height in this case, or I guess we could think of it as a width laying down, but that's in the y directions, isn't it? And so having an infinitely small x dimension, it has an infinitely small y dimension. And so that width is dy. Okay, let's put that dy down here. That's the width. I said height, I guess, but I'm still thinking of it as a width. Okay. Now, this time, though, the height or the length of that rectangle, what do? We take the highest, the largest value, okay, and the largest value is some x value, isn't it? See, it's an x value, and the lowest value is some x value. Okay, well, here's the deal then. This highest x value depends on the parabola. See, it depends on the parabola. So what we need to do is we need to take this y squared equal 1 minus x, and we need to solve it for x. I'm going to add x to both sides and subtract y squared on both sides. So that's another way we could write that parabola. Now, if we write that parabola that way, remember, we're looking at the biggest x value and subtract the smallest x value. Well, the biggest x value is defined by that parabola. And so we'll have the biggest x value, which is 1 minus y squared, and we'll subtract the smallest x value. Well, in this case, the smallest x value depends on the line, doesn't it? It depends on the line, where we are on the line. And so we look at the line, which is 2y equal x plus 2, and we solve that for x. So we'll subtract 2 on both sides, so we'll have x is 2y minus 2. So that smallest x value, being the line, solved for x here, is 2y minus 2. Now, I've kind of got that jammed in there. So let me kind of rewrite the whole thing so we can read it. Largest x value subtract smallest x value, and those x values come from our original definition of those graphs. We just solved each one of them for x, times the width of that rectangle, which is in terms of y. And you see, we have an integral in terms of y this time instead of x. But it's a much easier integral. We don't have to break it into pieces. So as we simplify the integrand before we try to integrate, what will we have? We'll have a negative y squared and we'll have a minus 2y, and we'll have a plus 3 dy. And remember, this ends up being the height, see, this, or the length of that rectangle, if you will, and the dy is the height. So when we multiply those two together, we get the area of that rectangle. Well, again, this is an easy integral. This is much easier than what we did a while ago. We don't even, in this case, we don't even have to think about square roots, do we? And you can verify this, but we'll get exactly the same result we got a while ago when we added the two different areas together, 32 over 3 square units. It would be easy for you to check, and I encourage you to do that just to make sure that you feel comfortable that we've done this correctly. Well, that's interesting, and we're going to, in fact, employ these ideas, remembering that this integration, we're always thinking about find something that we can define as infinitely small. Whatever we're trying to find, break it up into infinitely small pieces and use the integral to add all those infinitely small pieces together. And so it doesn't matter whether our rectangles are laying down or standing up. It just changes the variables being involved. Got one more problem in this section that I'd like to do, and so we'll do that on the next page. Okay, in our last example about finding the area between two curves, we turn to one that deals with trigonometric functions. Find the area bounded by y equal 2 sine x and y equal tangent x for x's between negative pi over 2 and positive pi over 2. Now, as I've done before, it's really critical that we understand what the graphs look like. And so let's kind of get ready to think about these graphs. Okay, so now we're only using x's between negative pi over 2 and positive pi over 2. So let's say this is where negative pi over 2 is. Let's say this is where positive pi over 2 is. So what we're looking for has to be between those two x values. Now, it is important to recognize what the graph of y equal tangent x looks like. And remember, in fact, y equal tangent of x has repeated periods, but one particular period does fall between negative pi over 2 and positive pi over 2. So that graph at least looks something, if you will, like this in between these two values. Negative pi over 2 and positive pi over 2 x values are in fact vertical asymptotes for that graph. Now, what about y equal 2 sine x? Well, y equal 2 sine x, we're talking about an amplitude of 2 for the sine function, aren't we? So it's going to go as high as 2 and as low as negative 2. And of course, at pi over 2, what is the sine of pi over 2? Well, that's 1. And so y would be 2 times 1, or 2. So what we end up, this actually ends up being a maximum position, doesn't it? So the sine function is going to look like this here. And then likewise, when x is negative pi over 2, y would be 2 times sine of negative pi over 2, and sine of negative pi over 2 is negative 1, so y would be negative 2, so we're at this position. And so it's coming down, and this, oops, didn't do that very neatly, I apologize, okay, something like that, okay. So here's the sine curve, and here's the tangent curve. Okay. So that's y is equal to 2 sine x. And this one is y equal tangent x. It would be nice if I had different colors there, wouldn't it? Now, you can see that we run into a problem, and we run into a couple of problems. But one of the problems that we run into is that we have two different regions that we're calculating the area of. But let me point out to you in this case, because we are very comfortable in the symmetry that the tangent function has and the sine function has, the area in this case, we could say is area 1 plus area 2, and we could think of this as area 1, and of course we could think of this as area 2, but because of the symmetry, and those two are the same, then it's really just 2 times either one of those areas. And I'm choosing 2 times area 2 because my x values are positive there. It just makes things work a little easier. It's my x values that I'm worried about, not so much my y values. So we need to be able to calculate the area of the region that we have right here. But now, one of the things that's important here is that we don't know we know clearly they intersect at 0. And so when we're calculating the area, when we're calculating the area of that second region, we're going to integrate starting at 0. That's the x value that we have here, but we don't know what this x value is. And that's where we stop our integrating. And so we've got to figure out what that x value is. Now we'll come to that in a moment. But we do need also to figure out, come up with the height of this rectangle, a representative rectangle in there. Well, remember the highest y value there, that's the highest part of that, the top graph, if you will, is sine of x. And so the highest y value, 2 sine of x, that highest y value is y is 2 sine of x. And the lowest y value, the one we're talking about here, is defined by the tangent function. And that's where y is equal to tangent of x, isn't it? So we're subtracting tangent of x. And of course, the infinitely small width is along the x-axis, is in the x direction. And so that's dx. And you see that we have our integral at least set up in terms of x's here. But we still don't know what this x value is at the intersection point. And so that's the next thing we need to concern ourselves with. We're going to come up with that value right there, okay, before we can do this calculation. So let's think about how we find points of intersection. Remember, what we're looking for is the x value that produces the same y value on both graphs, because both of those graphs have the same x and same y. So we're wanting to know what x produces the same y in both graphs. And that's simply a matter of saying, okay, well, one of the y's is 2 sine of x, and the other y is tangent of x. And so we need to know where those are equal. In other words, we're solving for x that makes this equation true. But one thing that we could do here is we could rewrite tangent of x as sine of x divided by cosine of x. And then we could clear the fraction by multiplying on both sides by cosine of x. So when we do, we'll have 2 sine of x times cosine of x, and on the right side we'll have only sine of x left, because we will have multiplied by cosine of x. Now, one way to solve a trigonometric equation is to get all terms to one side and 0 on the other and see if we can factor. So I'm going to subtract sine of x on both sides. So I have 2 sine x cosine x minus sine x equal 0. And in fact, on the left-hand side, I have a common factor of sine x. And so it can be factored out. When we factor sine of x out, we'll have sine of x times the quantity 2 cosine x minus 1 equals 0. I just factored sine x from both of those terms. Well, we have a product that's 0, so we take each of the factors, sine x being one of them, we set it to 0, and we take the other factor, which is 2 cosine x minus 1, and set it to 0. Because if either one of those factors is 0, when we multiply them together, we will have a 0. That's the way we could get a 0 result by multiplying. Well, remember, when is sine of x equal to 0? Well, sine of x is equal to 0 when x is either 0 or pi, isn't it? Or negative pi. So x could be 0 or some multiples of pi. But remember, we're only looking at x's that are between negative pi over 2 and positive pi over 2. So those we are outside our realm. And of course, we already know that x equals 0 is an intersection point of those two graphs. Just look up here at the graphs. They do intersect at x equals 0. Now, on the other hand, we need to solve the equation 2 cosine x minus 1 equals 0. So we isolate the cosine x by adding 1 and dividing both sides by 2. So we end up with cosine of x is equal to 1/2. Well, where does that happen? Cosine of x is equal to 1/2 whenever x is pi over 3 or negative pi over 3. Certainly cosine of pi over 3 is 1/2, and cosine of negative pi over 3 is also 1/2. So those are two values, and isn't pi over 3 in this interval? Yes, pi over 3 is smaller than pi over 2, isn't it? And negative pi over 3 is also in that interval because negative pi over 3. Okay, so here what we found is this point of intersection is negative pi over, where x is negative pi over 3, and this one is where x is positive pi over 3. That's really the one we're interested in because we're just doing the single region and then we're going to double that area. So we're integrating to a positive pi over 3. Okay, 0 to positive pi over 3. Well, now we're in business. Okay, now we're in business. We can deal with something. So, what is the indefinite integral of 2 sine of x? Well, it's negative 2 cosine of x. Whoops, I bungled that, didn't I? Negative 2 cosine of x. And what is the integral of tangent of x? Oh, that we don't know so well, do we? That we don't know so well. Well, it ends up being negative natural log of cosine x. Let's see if I've got that. Let's see if I've done that. Well, remember at the beginning of the semester I told you that there are certain integrals that you need to be familiar with, and this is one of them, that you need to recognize that the integral of tangent x, let me make a note of that. The integral of tangent x with respect to x is the opposite of the natural log of the absolute value of cosine of x. Now, that wouldn't be hard. I'm kind of getting off point here. That wouldn't be too difficult to show because we could think of tangent of x as sine of x divided by cosine of x. Okay? And then we could let u be cosine of x, and that would mean du, I'm doing this by substitution, would be negative sine x dx. So this integral would be sine x over cosine x, but that's a u. I'll say 1 over u. And we need a sine x dx, except it needs to be negative, so I'm going to put a negative here, I've got to have a negative here. So I'm going to have negative, and then this negative sine x dx is du. And so you can see that's the integral of 1 over u du is natural log absolute value of u, and we got a negative outside, and of course u in this case was cosine of x. Okay, so we end up with the integral of a tangent of x is negative natural log absolute value of cosine of x. And we're evaluating from 0 to pi over 3. But we already had this one negative in there, so that is, we had this subtraction that came from here, didn't it? And so we're actually needing to simplify, and we have what? Negative 2 cosine x plus natural log absolute value of cosine x evaluated from 0 to pi over 3. Well, first we substitute in a pi over 3. So we'd have negative 2 cosine of pi over 3 plus natural log of absolute value of cosine of pi over 3. Subtract what we get when we put a 0 in. Okay, well, when we put a 0 in, we get negative 2 times cosine of 0 plus natural log absolute value of cosine of 0. I'm sorry, I'm running out of space. Well, what did we decide? The cosine of pi over 3 is 1/2, didn't we? So we have negative 2 times a 1/2 in this first position. And again, we decided that the cosine of pi over 3 is 1/2. And so we have natural log of absolute value of 1/2, which of course is just 1/2. So we have natural log of 1/2 minus, now, negative 2 times cosine of 0, and cosine of 0 is in fact what? Cosine of 0 is 1, isn't it? Okay. Plus natural log of absolute value of cosine of 0. Well, cosine of 0 is 1, and absolute value of 1 is 1, so we have natural log of 1. So let me remind you that natural log of 1 is really 0, isn't it? So here's what we have. Negative 2 times 1/2 is a negative 1. So we have in this position, plus natural log of 1/2 plus a negative times a negative 2 is a plus 2, isn't it? And then minus a 0. Minus a 0, here we'll just say plus 2. So that ends up being what? That ends up being 1 plus natural log of 1/2. Now, I think that I've seen answers like this given in a little different way. But let me point out to you, I want to point it out to you here, that natural log of 1/2, so there's our 1 originally. Natural log of 1/2, well, that's the log of a quotient. And so that's the logarithm of the numerator, subtract the logarithm of the denominator, isn't it? And the logarithm of 1 is 0. So this ends up simplifying and just showing you another way as 1 subtracts the natural log of 2. And probably people would prefer that. And that's approximately, and we could go to several decimal places, 0.307, and we could go further decimal places. And so our area that we're actually